So this is topic 8, periodicity, 8.1, the periodic table. So there are 3 inorganic topics in year 12. There is topic 8, periodicity, topic 9, which is group 2 chemistry. They're the alkali earth metals, just next to group 1. And there's topic 10, which is group 7 chemistry, which is all about the halogens. So we're going to start off with periodicity, and in this particular session, which is quite a short one, we're going to look at 8.1, the periodic table. So I think back in, I think it was 1869, Mendeleev, he was the first person to be really credited for what we call the modern periodic table. It is all sorts of fantastic things, like leave gaps for elements that weren't discovered, and actually predicted the properties of those elements as well. But we're going to look at the modern periodic table because we know a lot more than what Mendeleev did back then. And we know that we can predict the properties of an element from its position in the periodic table. So the different areas of the periodic table that you need to be aware of are the alkali metals. And that's obviously group 1. You study them at GCSE. There is the alkaline earth metals. That's group 2. And you'll be studying that in the next topic. That's topic 9. Notice the term alkaline earth metals. So they form alkaline solutions, just like the alkali metals in group 1. But they're found in the earth, hence we'll call them the alkali earth metals. The transition metals, that's the area which is between group 2 and group 3, that big block in the middle. We're actually going to look at 2 elements within that particular block that are not actually transition metals at all. So you probably weren't told that at GCSE, but there are 2 elements there which are not actually transition elements, and we're going to look at those as well today. There is the metalloids. Now, the metalloids are things like silicon, so they're on the borderline between the metals and non-metals. It's those elements on that staircase between the metals on the left-hand side and the few non-metals on the right-hand side. Things like silicon. We've got the halogens, which we're going to look at in the next topic, topic 9. So that's group 7. And you've got the noble gases, which is group 0. When I was at school, we used to call them group 8 rather. The common term is group 0 now. That's because all of them don't have 8 electrons in the last shell. As helium, for example, only has 2 electrons in the last shell. Okay, so what we're going to do now is we're going to have a look at the areas in the periodic table. So these are the groups and the terms that you need to be aware of, but we have areas of the periodic table as well. So we've got group 1 and group 2. So if you imagine this block here is group 1 and group 2 in this block here. So as I begin to draw the periodic table here, you begin to take shape and you realise what the structure of the periodic table is all about. So this is group 1 and group 2 in this area here. And then you've got this bit here. So this is the transition metals. And then you've got another big block over here, like that. You've got one little element here, little element there, and if you've got quite a sophisticated periodic table, like an A-level version rather than a GCSE version, often you would see a block along the bottom there, and there'd be 2 rows within that. The 2 rows are the lanthanides and actinides. Now, I'm not going to write that down because you don't need to remember that, but I'll tell you that anyway. There's the lanthanides and the actinides at the bottom, and the reason why they call them these ones here, the lanthanides, is because they follow an element La, which is called lanthanium, and these ones are called actinides, just below the lanthanides, because they follow an element with a symbol AC called actinium. So your periodic table looks something like this. Now, of course, you need to know the names, and you probably knew them already, to be honest. But we need to know the names of the blocks as well. So this block here, we call this block the F block. Okay. This is called the D block. Will become clear in a second why we call them those blocks. You might have an idea already. This is the P block. And this here, that, and that one there is the S block. There's not 3 S blocks. That's classed as one block. Don't ask me why, but that is the S block. Now, we know what this element is, don't we? This one is, that's correct, it is helium, He. I can always hear you say it. And this one here is hydrogen. That one that we forget where to really put it. It's a bit lost there, isn't it? Can't decide where it wants to go, whether it be group 1, whether it be in group 7, okay? But that is what you call an S block element. So the elements are described in terms of their blocks based on their electronic arrangement. So it's the electronic arrangement which determines which block they're in. Let's give an example. So, for example, if you've got something like sodium, I always like to pick sodium. I know that sodium's got 11 electrons. So that is 1s2, 2s2, 2p6. You should know these inside out now from topic 1, 3s1. Now, sodium is an S block element, and the reason why that is because their highest energy electrons, so these are the highest energy electrons, are in an S orbital. So that's the highest energy electrons are in an S orbital. Let's pick a P block element. So I'm looking at this one here. This one is my favourite element. So it's all about the topic that we did previously. So we were doing organic chemistry. So this is carbon. So let's write C there for carbon. Now carbon has got 6 electrons. Nice easy one. 1s2, 2s2, 2p2. And we can see here this time that the highest energy electrons are in the p orbital here. So we say it is a p block element. Let's pick one more. So let's pick that one right in the middle there. And that one there is Fe, which is iron. Now, we know that iron has got 26 electrons when we get given the periodic table in the exam, so definitely don't worry about learning the periodic table. I've mentioned that before, please don't waste time. 1s2, unfortunately, when you keep looking at your periodic table like me, you almost do know it off by heart, but that's not something I've deliberately learnt. 1s2, 2s2, 2p6, 3s2, 3p6. You notice I'm going quite fast here, and that's because you're welcome to pause the video at any time, and you can go as quick or as slow as you like, and you can watch it as many times as you want, as long as you have a link. So it ends in 3d6, so it is a d orbital. So s orbital is an s block element, p orbital, p block element, and d block element for iron at the bottom there. And of course, if you were to write the electron arrangement of, let's say, I don't know, uranium with 92 electrons, you would find that the highest energy electrons would end up being in an f orbital. So we call that an f block element. I think actually there's only a couple of elements in the actinides which are occurring naturally. There's only uranium and thorium. The rest are only in really, really small quantities, to be honest, and they're quite difficult to get. And some of them are only manufactured, so they're only man-made. So thorium and uranium, or radioactive elements in the actinides. The lanthanides, you don't even learn this at university, actually. They don't do much, to be honest. The lanthanides, they all have 3+ ions, so they'll have the same charge, unlike the D block elements, which can have variable charges, like Fe2+ or Fe3+. The lanthanides, they all have a 3+ charge. Anyway, you didn't need to know that. I'm just throwing that little fact in there for you. So, now, I said a little something before. I said that, strictly speaking, that the transition metals and the D block elements are not the same thing. Okay, so the transition metals and the D block elements are not the same thing. So if I was to pick that element there in the very corner there, right? Now I'm going to tell you that that element there is scandium, Sc. Okay, so I'm not going to write down the full electron arrangement of scandium. I can do it in a shorthand method. So what I can do is I can look at what the noble gas is before scandium. And the noble gas before scandium, so scandium's got 21 electrons. So the noble gas before scandium is argon, which has got 18 electrons. So instead of writing 1s2, 2s2, 2p6, etc., then I can just write argon in square brackets like that, and that assumes that that's the electron arrangement of argon. And then what I'll do is I'll go to the orbitals after argon. So it's basically got the same electron arrangement as argon, 4s2, 3d1. Okay, so that's the electron arrangement of scandium. Now, scandium only forms 3+ ions only. So remember, if you have a positive ion, you've removed electrons. So this is a 3 positive ion, so I must have removed 3 electrons. So I'll move those 3 electrons there. So the electron arrangement of scandium is actually the same as the electron arrangement of argon, right? Now, argon, we know, doesn't have any d electrons. There's no d electrons. So there's no d electrons in Sc3+. Okay. So when scandium forms a compound, the ions in the compound are always 3+. The definition of a transition element is that they have to have a compound where there's partially filled d orbitals. Okay, so a transition metal is an atom that has an ion in a compound that has a partially, keyword there, filled d orbital. Okay, so we know that scandium can only form 3+ ions. So in every single scandium compound, the charge on the scandium is Sc3+, which will remove those 3 electrons there. There are no 3d electrons at all, so we can't have a partially filled 3d subshell. So scandium is not a transition metal. But it is a d block element. Okay, so it's not a transition metal, but it is a d block element. It has to be a d block element because it's got some d electrons in its atom. Okay, but this is a definition of a transition element, and that'll become very clear next year when you do inorganic chemistry and you learn about transition elements in a little bit more detail. Because transition elements have special properties. and scandium doesn't have that particular property. So I'm giving an example. Most transition elements, in their compounds, they have a colour. They're coloured compounds. For example, like copper sulfate is blue. Cobalt chloride is pink. So we know that any compound containing scandium, as long as it doesn't have a transition element in there, would have no colour. So I'd know that straight away because it's not a transition element. So scandium is not a transition element. And this one here, in that tiny little corner there, that one there is not a transition element either. That one there is zinc. Let's write the electron arrangement of zinc. So again, the noble gas just before zinc in the periodic table is argon. Argon has got 18 electrons. Zinc has got 30 electrons. Don't just take my word for it, guys. Look at the periodic table now. You should be pausing the video now and checking the periodic table when we're going through these things. The video itself might be quite short because I'm going through things quite quickly, but there's ample opportunity to pause the video and improving your notes. So zinc, if you look at the periodic table, has got 30 electrons. Argon has got 18. So we need to add on the rest of the electrons. The other 12 electrons. So we do that. So that's 4s2, 3d10. 4s2, 3d10. Now, zinc compounds can only form 2+ ions. So you can't get Zn1+ or Zn3+. So let's write down the electron arrangement of a Zn2+ ion. So if it's 2+, I'll remove 2 electrons. Now be careful here. We need to make sure that we're removing the electrons from the correct orbital. When you're making an ion, you take the electrons from the highest energy orbital. Now the 4s orbital is higher than 3d. We know that because that's a 4 and that's a 3. So I'm going to take my 2 electrons from there. I do not write 4s0. It doesn't make any sense. If I take the electrons out the orbital is not there anymore. So I've taken those electrons away and I'm left with 3d10. So the Zn2+ ion does contain d electrons. But let's have a look at our definition of a transition metal. A transition metal is an atom that has an ion in a compound that has a partially filled d orbital. Partially filled d orbital. Well, have a look at this d subshell here. We have 5 d orbitals in there, both with 2 electrons in there each. 5 times 2 is 10. All of those orbitals there, all 5 of them are full. They're not partially filled. Therefore, zinc is not a transition metal either. It is a d block element, but it's not transition metal. And again, if you think of any compound that contains zinc, what you'll find is that they don't have any colour. That's because they're not transition elements. We learn why transition element compounds have a colour when we do year 13 inorganic chemistry, when we look at transition elements in a little bit more detail. Out of interest, the letters here, D, P, F, S, they've got nothing really to do with the anything sort of technical in terms of like the letter in the alphabet or anything. Obviously the name of the orbitals, but the call them a P and the S and the D. It's based on when excited electrons fall back from one energy level to another when you heat up an element, and you learn a little bit about that in physics actually, in particle physics, but you don't really need to know about that here. Okay, let's just recap some reactivity trends. So we know that when we go down group 1, the elements get more reactive. And we know from GCSE the reason why that is. And that is because that electron gets further away from the nucleus as the group is descended. If it gets further away from the nucleus, it's less attracted to the nucleus. So less energy is needed to overcome that electrostatic attraction. So therefore it's easier to move, it's easier to react. You studied that at GCSE. Group 2 has the same trend, apart from you're removing 2 electrons this time to get a full shell. So the elements get more reactive again. If we want to compare group 2 to group 1, what you'll find that group 2 elements are not quite as reactive as group 1. There's actually 2 reasons for that. The first reason is that you have to remove 2 electrons in group 2. But also, if you compare, let's say, sodium is a group 1 element and magnesium is a group 2 element, magnesium, you not only have to remove 2 electrons as opposed to just 1 in sodium. Magnesium's actually got an extra proton. If it's got an extra proton, those electrons that you're trying to remove are going to be attracted more to the nucleus because you've got more of a positive charge in the nucleus because protons are positive. And they've got 1 more proton compared to sodium in group 1. Then it's going to take more energy to remove that particular electron. So that is what you would expect there. So you would expect that group 1 and group 2, they get more reactive as you descend the group, and group 2 is slightly less reactive than group 1. It'd be great to see that when I read your notes that you've got some full explanations there of why group 1 gets more reactive as you go down the group, and why group 2 gets more reactive as you go down the group, and why group 2 is slightly less reactive than group 1. I'd be interested to know whether you've picked that up there. So that's a trend within group 1 and group 2. The other trend that you need to know is group 7. So in group 7, the elements get less reactive as the group is descended. And that is because what we're doing here is we're adding an electron instead. So the trend is reversed. Okay. Now, there is some little anomalies rather here, hydrogen, and here helium. So there's a bit of debate in where to put helium. Often though, you would find that there's no gap here between helium here and the element which is below, which is neon. But sometimes you see a little gap. It's as if to say the person that's decided to write that periodic table can't decide exactly where it should go. And the reason why there's a little gap here is because helium is an S block element, but neon is actually a P block element. So you've got an element in the same group. One of them is an S block and one of them is a P block. Okay? So I suppose when you drew this out at the start, you probably thought, oh, that's easy, that's just group 1 and 2, and that's all of that's group 0, but actually no, you've got to look here, and all of that there is group 0, not just this bit. So the electron arrangement of helium, He, we've got 2 electrons, so that's 1s2, and if you look at the element below that, which is neon, so that's 1s2, 2s2, 2p6. So helium is an S block element and neon is a P block element. Another one, which is a bit strange, is something like hydrogen here. So hydrogen has an electron arrangement 1s1. So it's definitely an S block element. Sometimes you might find hydrogen just at the top here of group 1, over here, just above lithium in the periodic table. Because if you think lithium's electron arrangement is 1s2, 2s1. So it's an s block element again. And that's why you'd find that here, because it's got one electron in the last shell. However, the likes of lithium, sodium and potassium in group 1, they're metals and they're solid, but hydrogen is a gas. So you wouldn't often find hydrogen over here. You would sometimes, this is quite rare, but you do find it on occasion, especially slightly ordered periodic table. You might find hydrogen over here at the top of group 7, just above fluorine. And the reason why that is because hydrogen can actually form H- ions. It can form H- ions. Quite rare. They're called hydride ions. You will learn about that in Year 12 organic chemistry, actually, because it's used as a reagent in organic chemistry. So these are hydride ions, can actually act as nucleophile. There's a lone pair of electrons here. In fact, there's only 2 electrons in total. Had 1 electron originally, and we've added an electron there. So there's 2 electrons there, and we've filled the shell. So people often find that this element here can often be put in group 7, just like F- would be, or Cl-. There is another reason why hydrogen can often be put in group 7, and the other reason is that it is diatomic. Diatomic means 2 atoms chemically bonded together. Guess what? We know some other diatomic elements. We know that chlorine is diatomic, fluorine is, iodine is, and bromine is. Guess what? Where they are? They're in group 7. And you might think, oh, well, actually, hang on a second. Well, oxygen is diatomic. Why is it not in group 6? Or nitrogen is diatomic. Why is it not in group 5? Well, oxygen has a O double bond O. Nitrogen has a N triple bond N. These ones, however, all have single covalent bonds. So more reasons to believe that actually hydrogen should be in group 7. Additionally, hydrogen is a gas. So it's a gas, just like these. Obviously, we know this one's a liquid, we know that one's a solid, but there are gases within that group. It does follow the trend. We have an increase in boiling points and melting points from hydrogen. Remember, the next one's actually fluorine, then chlorine, then bromine, and iodine. So it does fit that trend. But the problem is, it's an S block element. And the likes of fluorine is not an S block element. So if we look at the electron arrangement of fluorine has got 9 electrons. So 9 electrons is 1s2, 2s2, and we can even count how many boxes, if you like, or elements are into the p block here. So when we count 1, 2, 3, 4, 5, we know there's 5 electrons in the p orbital. So it's 1s2, 2s2, 2p5. And we can check our answer by going 5, add 2 is 9. Fluorine has 9 electrons. That must be the correct arrangement. So this is a p block element, but hydrogen is an s block element. So there's some reasons there why hydrogen could be in group 1, and there's some reasons there why hydrogen could be in group 7. So to save all the arguments, we stick it there. All right. So that's the standard place for hydrogen now. That tends to be the standard place for helium. You sometimes see like a little gap there between there. And that's because that's S block. And that's because that's P block. Just to let you know that. And don't forget, remember, that hydrogen and helium are period 1. There's lots of occasions where I ask people, right, what period is lithium in? And they go, oh, brilliant, it's top left-hand corner, it's in period 1, group 1. Wrong. It's in group 1, correct, but it is in period 2 because the top row is hydrogen and helium, and that is period 1. Okay, so that was exactly 30 minutes. Please make sure that you keep watching that video. Make sure you know it inside out. Thanks very much.